Okay, so turning now to the implementation. So if you try to compile the handout code, then first of all, we want to do the cm.make thing now rather than just using a file. And that's because what cm.make is the compilation manager. And so what that does is it loads a whole project, including a whole bunch of files. And it does fancy stuff like trying to load the files in the order that makes sense for the dependencies and things like that. And so um, if we try to load this, then it's going to first load the signature, and that went okay, but it has trouble with the TreeDict structure because it says unmatched value specification, empty, insert, and lookup. And so what that's telling you is that the handout code here doesn't have an empty, and it doesn't have an insert, and it doesn't have a lookup. So we have to write those. Okay, so what I preloaded here was that there is this type of trees where a KV tree is a parameterized data type, which is either empty or node, where the node has a KV tree, a key, and a value, and another KV tree. So the idea is that you've got a node with a left, a key, and a value, and a right subtree. And then what this line says is that the type of dictionaries that the signature asks there to be is going to be implemented by KV tree. And so the intention here is that this is an abstract type or an unknown type in the sense that the client doesn't know that dictionaries are trees. And the way that that's implemented is that the tree data type is private to this code. That is, nobody can see trees except for the code in between the struct and end here where we're implementing tree dictionaries. Nobody else can see trees. And so nobody else can do anything with trees besides this code. So that means what we have to do is we have to basically tell the clients of this module about the things we want them to know about, which in this case we've said are empty and insert and lookup. So empty will just be another name for empty. That one's pretty easy. And then if you want to do insert, well, the type of insert says that it takes in order a comparison function, a dictionary, and then a key value pair. So it's going to take in a comparison function, a dictionary, and then a key value pair. And then we have to write some code. And so one of the things you'll notice is that I'm leaving off the types of these. So I could say that comparison takes k star k to order, and that D is a key value dictionary, and that K is a key, and V is a value. So you could put in those annotations of everything, but we actually don't have to. And conceptually, the reason that we don't have to do that is that we've already said that this whole package of code is supposed to have the labdict signature. And the labdict signature says that insert takes in those things. And so you can learn from that what the types of these things should be. Okay, so now how do we write some code to insert into a dictionary? Well, we, the implementers of this module, know that dictionaries are trees, and that's because when you're type checking an implementation of a module, you know this equation that a dictionary is a tree. And so we get to do things like case analyzing the dictionary as empty or node of left, let's call it k prime v prime for the key and value at the root, and right. So in the implementation, nothing's unknown. You're just kind of off to the races writing the same kind of code we've written all semester. So if we're inserting into the empty dictionary, then we want to make a node with two empty children and the key and the value at the root, and an empty off to the right side, because if we're inserting into the empty dictionary, we want that to be a dictionary that just contains that key and value, and that's represented by a tree like that. Okay, if we're not inserting into the empty dictionary, then we've got the key and value that we're inserting, we've got the key and value at the root of the tree, and then we have to figure out what to do. And to make this code fast, that is to make it have order log n or order depth of the tree complexity, log n if the tree is balanced, what we're going to assume is that the tree is sorted in the same sense that we talked about before the midterm, right? So when we're merge sorting trees, remember that what that means is that for a node, left and right subtrees, so for node LKVR, what we're going to say is that it's sorted according to the keys. And so what that means is that for node LKVR, L and R are each sorted, and every key in L is less than or equal to K, and every key in R is greater than or equal to K. Okay, so, and in fact, if we only allow a key to occur once in a dictionary, then unlike before, we can say that those are strict. And so the idea is that when you have a sorted tree, you know that every key that's less than the root is to the left, and every key that's greater than the root is to the right. Okay, that means that what I want to know in order to decide where to insert is to test how does K compare with K prime. And so there's three possibilities of the order there. It's either equal or less or greater. So if K is equal to K prime, then the spec in our signature tells us what we have to do. We have to make a dictionary where K, which is equal to K prime, now stands for the new value and everything else is unchanged. On the other hand, if it's less, then we know where to look to find K if it's there, or we know where to look to where we want to put the binding of K to be if it's not there, right? We look to the left of the root. And dually, if it's greater, then we'll leave L the same and do K prime B prime, and then we'll do our insert of KB into R. Okay, so if I've typed things okay, and then I do my cm.make, then, okay, good. So the code for insert is good, except we're still missing a lookup. All right, and how do we do lookup? Well, in that case, we just get a key. And remember that what lookup is supposed to do is it's supposed to take a comparison function, a dictionary, and a key and return a value option. And so because it's curried, I write things like this. I write comparison function space D space K. If it were not curried, then it would look like the usual pairing or something like that. But since it's 3 curried inputs, it looks like that. For insert, it's 3 curried inputs, one of which is a pair, so it looks like that. Okay, and so again, we're in the implementation. We know exactly what dictionaries are implemented as. And so on. So if we're looking up in the empty dictionary, then it's not there. And the way we're supposed to signal that it's not there, remember, is returning none. And so if we're in a node, then we want to look up k. Well, again, we can compare k with k prime using the higher order function that's an input here, right? So the comparison function that we're passing in is telling us how to compare the two keys. And so the possibilities are that they're equal or less or greater. And if they're equal, then hey, we found it, v prime is what we want. And otherwise, we know where to look. I want to look up k on the right in the last case, or I want to look up k in the right in the other case. And okay, cool, that worked. Or at least that loaded. All right, so the thing to observe about this code here is that when we do an insert, we're assuming that the dictionary is sorted. When we do a lookup, we're assuming that the dictionary is sorted. So the question is, why do we get to assume that dictionaries are always sorted? And this gets at the idea of what's called a representation invariant. So the idea is that the lab-dict signature just tells you there is a type of dictionaries. There's an empty dictionary, there's an insert function, there's a lookup function. And in one of the next homeworks, we'll extend this with a merge function that has some additional functionality. You might want other functions and so on. But the point is that the only operations on dictionaries are the ones that are specified in the signature. From the client's point of view, all you can do with a dictionary is what's specified in the signature. So if every operation on the signature behaves nicely with respect to some invariant, like the tree being sorted, then in some sense you're good. And contrapositively, if the invariant is ever broken, you know exactly where to look. If you ever see a tree, a dictionary that's not sorted, then it's either empty or insert or lookup's fault. And in some sense, we can rule out lookup because lookup isn't producing a new dictionary. It's really just empty and insert, which are the potential problem, because those are the ones that are outputting dictionaries. So in order to convince ourselves that in any program we'll only ever see sorted dictionaries, we get a very strong reasoning principle, which is that it's enough to just look at empty and lookup and insert. And so empty is producing a sorted dictionary because, well, I didn't say it up here, but empty is sorted, sort of by definition. And then for a node, there's some conditions. And so then what we have to think about is these. So why is this sorted? Well, here, k was equal to k prime, so we didn't change the keys at all. So if it was sorted before, then it's sorted after. Here, by induction, this is a sorted dictionary and contains L and potentially a new binding of K. But the whole thing about this test here is that the comparison returned less, which means that K is less than K prime, so it's on the correct side. And similarly, if K was a new key here, it goes in, but here, exactly what the test said was that K was greater than K prime, and so K is going on the correct side there. Okay, so because we can check that our insert function does the right thing, we know that we'll always see sorted dictionaries. And if we ever see a dictionary that's not sorted, then we can point exactly to the code where there's a potential problem. It's either empty or insert. So the representation invariant idea is that if you keep a type private to a module, then any invariant about the values of that type is maintained or broken only by the code from that module. So the fact that trees are sorted is the responsibility of this module and nobody else. Okay, so now if we go back to our client code, we can try our increment function. So for example, if I do increment TreeDict.empty of the string hi, then I get a dictionary with hi in it. If I do increment again of that dictionary with the string hi, I get a dictionary with two highs in it, right? So notice that I didn't get two highs in the tree. Instead, I got that the one high key maps to the value 2. If I put the value there in it, then now I have high in there. There's a little bit of a fiddly thing, which is that by default, SMLNJ doesn't print things all the way down because sometimes the values get spit out on the screen get too big to read. So if you want to change that, you can do the control.print.printdepth := 100, which sets the print depth to 100. And so then we can see the tree a little bit better. So the tree that we get by incrementing high twice in there once is high in there. And note that the there is to the right of the high, which is the sorting order that we specified there. If I put an A into the tree, then I get an A to the left of the high, which is in the middle, which is there. Okay, so that's how that all works there. So the main takeaway here of thinking about the implementation is that the implementation is a nice example of a representation invariant where the responsibility for making the tree be sorted is kind of all up to the implementation of TreeDict. The client code over here in count can't really break that if the TreeDict implementation correctly maintains it. Then since this client code, all it can do is call inserts and throw in some empty dictionaries and so on. If those are all good with respect to whatever property we want the data structure to have, then the whole program is good overall. Okay, so you can look at the lab solution for like the solution to the count function, but it's basically just a loop that calls increment a bunch of times. So nothing too fancy going on there. All right, so that's a bit more tutorial for how modules work, right? So we've seen that the types in the modules can be parameterized. We've seen examples where the functions in the module take hardware functions as input. Then we get packages of code that kind of all work together about an unknown abstract type of dictionaries. And also specifically, you've seen how dictionaries could be implemented with what's called a binary search tree is the tree structure that we're using here, and how insert and lookup work for that. So this is really leading into the modules homework and the final project, which will make pretty heavy use of dictionaries, but we'll keep going with that a little bit next week. For next week, the main thing to focus on is getting your Barnes hut done. So thinking about more about sequences for now. Okay, talk to you all later. Bye.